Okay. Hey guys, hope you all are good. Very good evening. So we are going to start soon. This is a YouTube video and it's going to be on cycle detection in directed graphs. So most of you would be knowing that this is one of the most frequently asked interview questions. And in this session, we are going to see this, that how we can do cycle detection and how basically it compares against the same kind of procedure, cycle detection, in other kinds of data structures like undirected graphs or linked lists or whatever. Okay. So you all might have already seen cycle detection, how it is done in undirected graphs, how it is done in linked lists, and you might be having a fair enough idea about it. So if we have a kind of memory and if we do a kind of traversal, then it comes back. So anyway, let us very briefly then revise how it actually takes place in undirected graphs, and then we will come to what needs an extra attention in directed graphs. Let us visit all those things that actually form the sub questions or maybe subtopics in an interview discussion. And by the end of the session, what we will be having as objective is you all will understand that how to find a cycle, how to detect a cycle in a directed graph. This would be our final objective. So that's fine. I think we should wait for 2-3 minutes till everyone joins. Cycle detection in directed graph. So this is our agenda basically. First of all, we will revise this procedure in directed graphs. Sorry, undirected graphs. We'll understand where exactly we need to do different in directed graphs. What is the extra attention we need to pay? So we will understand the differences. Understand differences. Just a second. Understand the differences with directed graphs. And then proceed for the implementation. Make sense? So that's it. We'll be starting at 6.3. Okay, it's 6.3, so let's begin. So cycle detection is something like this. Suppose we have some undirected graph. Let us first look in terms of undirected graph. It's something like this, that you have nodes and definitely you may have some root, you may not have some root. I'm sorry, we said undirected graph. So basically we don't have root, suppose. It is an unrooted tree. So we have some structures in this manner and there can be many different things. At some point of time, there can be some odd or even cycle in the way, and there may be many other nodes. So the thing is that basically if we start moving from a node such that when we come over here, we don't come suddenly to the parent. We will keep on moving away from this node. There is a chance that we can come back to the same node. This is basically what cycle detection means. So if you move in this manner, clockwise, anti-clockwise, however you choose to, and if we come back to the same node without repeating any edge, then that is what we over here refer to as cycle detection. Now you can also say that, okay, these are undirected edges, so I can choose that I'll go over here and then I'll come back over here. It's fine, and conceptually it is not wrong. But over here we are concerned about those cycles where we don't repeat any edges. So cycle means no edges are repeated. No edges are repeated. So no edges are repeated, and what will happen? If you start enumerating the cycle, enumerating means if you start labeling the cycle, you have to basically start from the first vertex. You have to go on writing the vertices, and basically your starting vertex is going to be the same as the ending vertex. It can be either of them. You can maybe like if they are 1, 2, 3, 4, 5, 6, 7, 8. You can refer to the cycle as 7, 8, 3, 4, 6, 7. You can refer to something like 7 to 8, like there are 5 edges. This is what it represents. 1, 2, 3, 4, 5. Okay, it totally depends. Like you can find computer programming questions where they will ask the representation in this particular manner. That okay, you're starting from some vertex and you're roaming around the cycle and coming back to the same vertex. So they will ask what are the vertices you visit in that cycle. Once you state the vertices, it is a deterministic way to indicate that what your cycle actually is. It will tell you that okay, your cycle goes like this, from 7 to 8, then from 8 to 3, then from 3 to 4, then from 4 to 6, then from 6 to 7. So that's about a cycle. Now the question arises, how to find it out? It happens that in undirected graphs it is fairly simple. The only thing that comes that we need to be careful about is, suppose there is a vertex like this, and there are 2-3 vertices which lead to this, and there are another 2-3 vertices which lead to this. The thing is that if you are already visiting this vertex, suppose you started visiting from here, you visited this vertex and then you proceeded some long paths. You traveled some long paths and you discovered there is no cycle. Then you started traveling from here, suppose. You need to be careful that if it has been visited, you should not visit it once again. How can it be ensured? In undirected graphics, you can ensure that after you visit everything like this, you can directly visit over here. You can directly visit and you can basically cover a single component in one traversal. You can say if it is a component and it is an undirected graph, you can travel in all possible directions. And if there is a cycle, suppose something like this, it will always happen that suppose we propagate from here, it will always happen that at the end we will some way come back to this one. Okay. So when we are traversing away from this, before we are finished with everything, we must always return to this point. This is the rationale which is applied in case of undirected graphs. Let us see an example to understand it better. So we have 3 nodes till now. We have something like this. Suppose here it is joined. Suppose they are joined over here. And there may be like other nodes as well who are over here. Okay. Now basically the way it runs is, start from any single point, start from over here suppose. This one you can visit and then you can say okay, I'm coming back, I have not seen any cycle yet. Then you will visit this particular thing. You will visit maybe something like this, you will visit over here, you will come back, you will visit over here, you will visit this, and when over here you visit this particular, you see that it is repeated. Now over here, identify this, that you are not using its parent, you are not visiting its parent, you are visiting some other node, and that node happens to be a node that you have seen earlier from where you have started the journey. Now the thing is, what if I say that from here you started but it is not exactly your parent? What if I say that this is not the path, it may be like there is no such path, it is only that you have seen it before at some other place, maybe it was in some other component. What if I say that this is X, this is Y, and I am seeing that I have visited Y? What if Y was in some other component? In some other component? So what is the possibility that X to Y, you find that Y is visited, but still it will not form a cycle? What is the possibility? What is the possibility that okay, I have reached from X to Y, I understand that I had visited it. What is the possibility that from here we won't find a cycle? The only possibility is that there is no path. There is no path, which means it must be in some other component. If it is in some other component, I cannot visit from X to Y. What can be another possibility? Maybe from there while doing DFS, we have not reached X. While doing DFS from X, if we don't reach X, then this particular cycle will not form. But I hope I am audible through the duration. Okay. So If I'm not able to reach here, then what can I say? From y, if I'm not able to reach x, that means from y, x is not reachable. I know that I'm visiting x beforehand. From x, I'm checking that okay, y has already been visited. So this indicates that from y, definitely there is a path. What if I say, okay, I might have visited from x, I visited something else. From there, I visited y. That also might have happened. So whatever that is, then also I can say, okay, it is a cycle at that time. You can understand that now we are discussing about directed graphs. So if I am visiting this and if I see that it is already visited, what are the chances that while doing DFS from y, I ended up over here? Or the second chances that maybe from x I stepped into something where I had formed an edge with y, and now from x also there is an edge to y. Whatever is the case, you can always see that there is a cycle which is forming. There is always this closed loop kind of a thing which is forming, however you see it. And hence, we say it cannot happen that it is in some other component. This possibility cannot happen. So we are ensured, like we are confirmed that if we do a simple DFS, we are always able to do cycle detection. Why? Because if I see that from any node y, I am able to reach a certain node x, which was already visited. Before visiting it, it was already visited. Then I immediately know that this is forming a cycle. There was some way in which they were connected before, due to which after being visited I can still come over here and then I'm able to connect it. So this is how a cycle is formed. It's a simple DFS. Okay. What is the time complexity? That's simple. Order n, because I think order n plus m, because we are reading the nodes and the edges and we are performing a DFS, so DFS takes order n plus m time. So this is basic cycle detection. How can we take this idea forward in directed graphs? This is the main agenda for today. So how can we take it forward for directed graphs? Let us understand it through some directed graph and let us analyze what is the difference. Suppose I do the same thing. Suppose I do the same thing for a directed graph. Same thing means I may say that okay, same thing means this is maybe my parent, I am having some directed edge. So I started DFS and I proceeded in this direction. Then I started some DFS and I am reaching some node from where I am reaching this. In the same manner, I can say this is going to be a directed cycle. This is going to be a cycle, just a second. This is going to be a cycle, can we say? Because we can start from here and we can reach back up to here. So it is logically a cycle. So in this case, we are getting this answer using BFS. So using DFS, we are able to get the answer. We started from this node, we traveled outwards, and traveling outwards, I have come back to this point. What if the situation is slightly different? What if the situation is something like this? We have this, and over here, maybe you have something like this. What does this say? You can do suppose a kind of DFS. Is there any cycle? No. You can see that in this direction, if we keep on going, this is the maximum we can go. We cannot go this rest of the part. This is in some other direction. So it is not a directed cycle. So this one is a case of no directed cycle. There is no directed cycle in this. So when we are talking about cycle in a directed graph, we are only concerned about directed cycles. So this is an interview question which has been asked in FANG companies and also in many other companies. And this is treated as a very important interview question. And through this actually many concepts, many observation skills of the students can be assessed. Okay. So do watch and do follow the rest of the discussion with with importance, with significance, with sincerity. Okay. So try to see there is no directed cycle over here. But the problem is if I do some DFS, then the problem is when I'll visit this node. The thing is, if I visit this node, I can say I'll be visiting this, I'll be coming back, then I'll be visiting this, I'll be visiting this, I'll be visiting this, and I'll be visiting this. When I visit this once again, I'll see that it is visited. Using this information that it is visited, if I say that there is a directed cycle, won't it reach me to the wrong conclusion? Won't it tell me that, okay, there is no directed cycle, but this is wrongly giving us the impression that there is a directed cycle? That is exactly the observation over here. We are getting a wrong impression of a directed cycle. Okay? So what can we take from here? Suppose I say that, okay, I won't be using the visited then. What I'll be saying is that instead of visited, I will see that if I've started from here, I must be reaching up to here, or what can I, okay. So I'll not be using visited. Then first of all, before whether I'm able to calculate or not, how I'm able to see this, just leave that for a while. But think about the time complexity, that what will be incurred. I know that I won't be able to reach this. I know that this is not a part of any directed cycle. I understand this. Suppose some other node is also attached to this. Suppose some other node is also attached to this, or maybe attached to this one. What can I say over here? Here also can I say that, okay, or maybe suppose it is attached over here. Now from here we have visited this and we understood that this is not a part of any directed cycle. And from here when we are visiting this, in order to understand whether this is a part of a directed cycle, again we have to do a pre-computation. So if we are not using a visited array, then if we don't use a visited array, we have to do some recomputation over here once again, because this node now has no labeling. This does not remember whether it is visited or not. So what I'm saying is I'll be using some visited, but when I'll be leaving this node, suppose I visited over here and then I'm leaving this, suppose I change this visited to 0. What will it indicate? Suppose I've changed everything such to 0. Suppose I've left this and I've changed everything to 0, that I haven't visited them. They are all 0 now. There is no cycle, I haven't visited them. I've changed everything to 0. Now from some other node when I'm visiting it, what can I say? That okay, now I can see that there is again no cycle forming over here, but I have to spend again these many nodes time. That is double the time. For the single node I have to spend double the time now. Why? Because I have already visited them. I should know that I should not waste any time here, but unfortunately I'm wasting some time. Does this make sense? So what I told here over here is that suppose you don't use a visited array, then the problem that suppose you don't use a visited array, if you don't use any visited array, then the problem is you cannot find out the directed cycle or any cycle. If you use a visited array in order to detect the parent, what I'm saying is if you cannot detect, suppose you come from here, you end up to here and then you cannot detect anything, then while going back, make them as zeros, everything. Why this is important? So that if it happens like this, that from here you visited this guy and then from here you are again visiting this guy, when this guy from here you could not visit anything else, you should mark it as 0, that okay, treat me as if I have not been visited. And then while you're going from here, you will see that okay, this is not a problem for us, like because this guy hasn't been visited. But there is something, the moment you say this, you are doing one good thing. You are preventing the detection of such entities which are not cycles. So you are preventing that one mistake from happening, but you still don't know whether all the cycles you can successfully detect or not. We can show that okay, cycles will be able to detect. How? If there is such a kind of cycle, we will always say that okay, from here, from somewhere we'll be visiting this, we'll be visiting all these, and by the time we'll be reaching over here, they all will be labeled as 1. When do you label as 0? You'll be labeling the vertices as 0 or the visited array as 0 only when just a second, yeah, you will be labeling this as 0 only when you are leaving that. So you have completed DFS from that node, and when you're leaving that, only then you should change them to 0. Got it? So using this rationale, the thing is you'll be able to find every cycle. So this rationale which I described, that visited will mark 1 if a vertex has just been visited, or maybe we can say he has been visited or has not been left. Okay, they have not been left yet. So from here what can we say? not been left, when we know that it has been left, we should mark it 0 so that a false negatives like false directed cycle does not get detected. Up to here I think it is clear. What next? Now what can we understand from this question? That this can lead to a lot of extra time because we are marking it 0. Whenever it is being left, we are marking it 0, so it can lead to a lot of extra time because many things, many nodes might be pointing to me. From myself, I cannot reach every one of them, but from them I'll be able to reach myself. So in order to tackle that kind of a situation, or basically to avoid the wastage of time over there, I can say that let us maintain 3 pointers, or basically 3 kind of states. One state is state 0, suppose. We'll maintain a number of steps, and these are the states. These are the states which are important to us. So the three states which are important to us are unvisited, visited but left, visited and still active, Why? When I'm coming to each of these stages. Active, and last one is visited and left. Okay? They have been visited and then they have been left. Let us understand the differences. Unvisited means, you understand, I have never visited. Unvisited means basically it means that I have never visited that particular node. So it will say that, okay, that node has never been visited. What is visited and left? That means the DFS is over. What it means is, suppose I started from here, I visited all the children and I covered everything. I didn't get any cycle. Okay, I covered everything, I roamed around everywhere, and then I'm coming back. I said that, okay, I can't find any cycle. Then I'm going to leave it. I'm going to leave it for some other node. That, okay, its job is over. Now somebody called him, I'm going to return the control back to him. So that, then this particular node which I'm leaving now, this particular node X, I'm going to call it within this visited and left. Means DFS from this node is over. DFS from this node is over. From this node is over. And this means if you're leaving a vertex, then this means that this node cannot be a part of any directed cycle. Why it is so? There are two cases. Suppose it forms a directed cycle and its parent is connected to it currently, okay, which is a part of the directed cycle. Suppose it is something like this. You can say, if this is a part that it forms a directed cycle like this, and you have reached this node X, you can like extend the DFS from here and you can connect it over here. Once you connect it over here, you have a total cycle with you. What is the other case? The other case, suppose this parent is not involved. You have a cycle with this parent, but some other parent involved you. Some other parent called you. Okay? Suppose this one happens. Some other parent calls you and you form it with some other guy who hasn't called you yet. Okay? So you have visited this one, you have visited this one, you have visited this one. And these are some other guys. What can you say? While you will do DFS from here, if there is a directed cycle, you are definitely going to visit these nodes. This node will definitely be visited. From here, this one will also be visited. From here, again, this one is going to be visited, and we know we are going to get the cycle. So that is exactly the idea. So if any directed cycle exists of which this is the part, we will always be able to form a cycle. But if the DFS completes and we are not able to form it, then we say that it now transitions to the state of visited and left. Okay? It transitions to the state of visited and left. Why? Because DFS from this node is over. What next? Okay. Now the second state is the most important, that is visited and still active. What does this visited and left actually help us in? Suppose you have left this vertex. Okay, you have left, like if DFS from this vertex is finished, everything is finished. Now from another vertex you are visiting it. You can say that, okay, please don't come to me because I can't help you in the formation of any cycle. If it turns out that, okay, a cycle did exist, I could have myself reached you. but I could not reach you, so just forget about me. You can't reach me. That is the idea. Make sense? So this is my idea when I say that okay, I'm being visited and left means now I cannot be part of any cycle. So we are able to reduce the computation over there. The moment I see from some node that okay, this guy has been visited and it has left already, the DFS has left it already, that means don't visit it once again. So this state has a very special implication to me, which the other states don't have. Unvisited means it still needs to be explored. Visited and left means it needs to be explored. There is no cycle, it is not alive, but it needs to be explored, something like that. And visited and still active means that now if you anyhow get into this, active means that you actually have started DFS from here and you have come back to some point from where you are again reaching this. So basically if you have started DFS from here and if you like are roaming around in its subtree or whatever you call it, below it, like ahead of it, and then you can say that this basically is contained in this particular state, visited and still active. Hope that makes sense. So we are forming three states which are disjoint among themselves. There is no node which can belong to all the three states. So let us try to understand it. Suppose this is state 0, this is state 1 and this is state 2. Let us try to understand it, how it basically like happens, how it basically moves. Suppose first of all we say that there is no directed cycle. Okay, so this is not a directed cycle, and then we can say okay, there may be even something like this. There may be something like this. So there is no directed cycle. You can see there is no directed cycle. Now let us explore. Initially all the states are 0. All the states are 0. So there is 0, 0, 0, 0, 0, 0, 0. They have not been visited. Now I say I'm going to start from suppose this node. Okay, and I'm going to mention it as 1. That is, now this is visited and it is active. Now I started DFS from here. I started from here. Suppose I reach over here and I say okay, it became active. Now I want to do DFS but I cannot do any longer. So I'm going to come back, and when I'm going to come back I'm going to say that okay, it has been visited and now I'm leaving it. So change its state to 2. So now this node is active. This node has been left, so it is in state 2. All other nodes are unvisited. Now suppose we are going to visit some child. Suppose from here. So we are going to change it to 1 because this has been visited. Why didn't I change it to 2? Because DFS is still running. DFS is still running from this node. That is why I did not change it to 2. Now I came here and I've changed it to 1. 1 means visited and still active. From here, suppose I come to this particular stage using DFS. I say that okay, it has unvisited. Fine, let me change it to visited and still active. I'll change it to visited and still active. Same thing when I come from here to here, I'll do the same thing. I'll change it from unvisited to visited and still active. From here I come over here and I say that okay, do the same thing, visited and still active. Now I'll say that okay, I can't proceed any longer. I can't proceed any longer. From here I don't have any outward edge and hence I can't do DFS from here. So what will we say? Leave this node and mark yourself as visited and left. So it will mark itself as visited and left, state 2. It will come back over here. This guy will also say I can't do DFS any longer. I did not find any cycle till now. So it will mark itself as 2. It comes back. This guy says that okay, I could not get any cycle and I have to leave now. So it marks itself as 2. It leaves and over here, now it says that okay, from here I had visited this node. I did not visit this node. From here I did not visit this node. So let me now visit this particular node. When it visits this node, what will it see? It has got 2. Which means this guy indicates that it is a failed candidate. It cannot be part of a cycle. So I should not spend my time behind some unnecessary computation over there. So it will say that okay, I cannot proceed to you because you are at state 2. You are already sort of dead. You are not involved in the process. So let me leave it. So now it says that there are no outward edges. It just returns. Where shall it return? Somewhere over here. It will return it, saying that I have to change myself to state 2. Now you can see this entire part is dead. This entire part is dead. So this is one important thing. From a certain node, if you are traversing through DFS and you are reaching certain nodes, all of them will become dead before this guy becomes dead. Before this guy becomes dead, this entire subtree has to become dead. It must happen. Why? Because from here you are actually visiting all these nodes. Make sense? Okay, so now when we get back over here, what can we say? That this guy still has this one child remaining, so it will call it. It traverses, like it transitions to the state 1, and then it says, okay, let me travel to my neighbors. It travels to its neighbors, it says this is already dead. So this is like a dead state. This is like a dead state. What is this state equivalent to unvisited means? It has not yet started, so it is maybe ready to be started. It is ready to start. And this one means it is active, it is running. So you can think of like the OS states, you might remember operating systems. These are actually the states. So you can compare them to these states. Once you leave a node saying that this node cannot give me any cycle, this is dead. So from anywhere else, if you come over there and if you say I want to explore again, you'll be wasting your time. So to prevent the wastage of time, we did something like this. Make sense? So this is how we are going to find this. We are going to reach this conclusion that there is no cycle. Suppose there is a cycle. Let us see how it occurs in such a graph. Suppose there is a cycle like this. And suppose we come here from some other parent. And yeah, and maybe over here you have something like this. Okay. So this is something, suppose this is the route where we are going to start from. Let us see what happens. Initially, once again, all the colors are 0. So you have visited. All these are visited. Now what we can say is, we'll start from here, so we'll mark this as 1. Then we go to its neighbor, we mark that as 1. From here, just a second. Okay. From here, we are going to travel to its neighbors. We'll mark them as visited. From here, we are going to travel to its neighbor. We'll mark it as visited. We are going to travel to its neighbor, mark it as visited. From here, we cannot travel any further. From here. Okay, did I fail to create a cycle? Okay, maybe I wanted to keep it different. So, right. Instead of that particular edge, have that edge in this particular manner. Okay. So now see, you have this cycle as well as you have the outer cycle. Let us see how we proceed. From here we have visited this node, so we are changing it to 1. And from here we are visiting that particular node, so we are changing it to 1. Now from here, suppose we are visiting this particular node. If you are visiting this particular node, then also we are finding a cycle. And from here, if we visit this particular node, then also we are forming a cycle. So you see, if we are visiting from here to here, we are seeing that it is 1. 1 means active. And what does this indicate? That if I join with you, since you are active, from you there exists a path which comes to me. So it is a cycle. Similarly, it can do the same thing with the other node. It will say that this is 1. So go over there and declare that you have found a cycle. So this is basically how you can say that, okay, there exists a path from that node to this node already. So when you join another edge in the opposite direction, you are getting a cycle completed. So the same process, using the same things, you are able to identify a cycle. Make sense? Here also, while you are finding a cycle, it may happen that some nodes become dead in the process. It doesn't hamper, like it can happen like this, that there is a cycle like this, and then all these things are there. So from here you start, you go up to here, and then you come back and you declare this as dead. So this is dead. Now you come back to here and you complete this process. So you're getting a cycle. Okay. So you can understand these 3 states are sufficient. And that is it. These are the states, the understanding around which all your interview questions are based. So now if there are no confusions, we will shift to the coding. Let me know, are there any doubts? Is it clear, or do you require any other example? Do you require a re-explanation on why these states are absolutely essential? Like these states are not redundant, you can't do with 2 states. That is what we proved at the first time. So even like in one of my interviews, I had been asked the same thing, where the question was explicitly that why can't we do with a single visited boolean value, true or false, and I just had to give him or her the intuition how it worked. Okay, so that is exactly the style of questioning. We can move ahead. Just let me know if it is clear up to here. Is the idea clear how we are utilizing these states in understanding? We'll move on to the coding implementation and it will become clearer. Or you can ask any questions. At 6:36 we'll be shifting to the coding. Maybe till then I can do something. Let me know if you have any doubts, and till then let me tell you about the batches which are going to be offered at Unacademy. And don't run away. This will take just 1-2 minutes, I guess. So these are 4 batches which are being currently offered at Unacademy: Transpire, Eklavya, Brahmastra, Mahayodha. Transpire is on CS Fundamentals, OS DBMS Networking Master Course. All these you can see they started on 20th or 21st July. You get a structured learning path using these batches, one subscription and unlimited access to all batches or courses. You can crack interviews at top product companies, best coders of India's educators, and all these. So in batch structure of Transpire, you have something like this. You have networking, you have databases, you have operating systems, you have OOPS. And in Eklavya, you basically have building blocks, that is beginner level programming, then the intermediate level, then the advanced level concepts. Then you come to Brahmastra 3.0, where you basically have some beginner intermediate topics, and then you get some advanced topics, but they will be totally pertinent for your interviews, placement things. Like we are discussing the problem today, you will find everything compressed over here. In graph algorithms, you will find these. Okay. Then we come to Mahayodha, which I am taking currently at Unacademy. So it has only the advanced programming concepts, advanced dynamic programming, segment trees, advanced concepts of graph theory, mixed problem solving. These are some of your educators. You have ICPC World Finalists, Code Forces Grandmasters, and the top product companies. And you have live interactive classes, practice relevant problems at CodeChef, and doubt support. Doubt support in Discord with your TAs. So you can look at their profiles, and this is the pricing. 1 month you need to pay 6,000. For 12 months you need to pay 33,000, and it is quite discounted. You can see you can get an additional 10% discount on top of this by using my referral code Saptarshi1729. When you use this referral code, you get an extra 10% discount on top of all these. Okay, and these are the campus placements, IT jobs. So 360-degree support to crack TCS, Infosys, Cognizant, and other exams. They'll be taking this batch. Okay, this is the Achiever batch and the Hall of Fame batch. You can fetch the details from here. Okay, so you can prepare for dream companies such as Deloitte, Ernst & Young, Samsung. Okay, cool, that's it. So if there are no doubts, we can shift to the coding. Shall we? Tell me guys if we can shift to the coding. I'll be waiting. If you have any doubts, you can ask. Else we'll basically show how using only these states we can solve the entire question. So you can indicate if you have any doubts. Any doubts, guys? Shall we proceed to the coding implementation? Yeah, hi Atul. Shall we proceed to the code, guys? Maybe a simple yes, no. If you want me to re-explain, you can ask, or you can tell me to if I can move to the code. I'll be waiting for that. In my live classes, I've never liked non-interactiveness. So let me know what you want. explain. Okay, there are three states. I'll explain it in very brief. There are three states. In your undirected graph, you just need to maintain two states. Either it is visited or not visited. When it is visited, you start from there, and if you see you're coming back to it, then you declare that you have found a cycle. In a directed graph, it may not always be the case, because over here you can see you can come back to this, but here the direction is different. So this is not a cycle. Here you can come back to this, but it is not a cycle. So over here we maintain three states, saying that we maintain visited, so that if a node is a part of has already been visited but there is no cycle around it, if we visit it another time, then we can understand that it is not a part of a cycle. So we won't be performing DFS once again over there. So visited acts as an indicator for us whether we are going to perform something. But if we see that okay, it is in state 1, that is visited and still active. If it is visited and still active, that means it has been visited and we started DFS from it, and we are in the process of that DFS. If in the process of the DFS we again get back to it, that means there exists a directed cycle. But this does not happen over here. Over here you can say that I'll be visiting maybe this guy, and then I'll be coming back and then going over here and then visiting this guy. So over you can see you are coming and then leaving it. If you are coming and leaving it, then it belongs to state 2. So we are discriminating the two states. One is it is unvisited, you have never visited it. Another is it is visited and it is still active. That is, if you reach there, then it has been one of your ancestors. So if you are reaching over there, it will definitely complete a cycle. But visited and left means something like this, that you visited it, you visited over here and you visited a very long route, all these, everything what is below, you have visited them, and you have come back hopeless. You have come over here, from here maybe you went to some other node, and from here you are again visiting it. Suppose there is again an edge. When you visit this, you don't have to cover this once again. You can avoid this repetition. If you cover this, if you go over here once again and you search for cycles, you won't be finding a cycle. You cannot find a cycle over here because a cycle doesn't exist. So that is why we form two states. If this state stores a value of 2, this indicates that when I come over here, I'm not going to get anything. 2 means I'm not a part of a cycle. Okay? In short, this is what it means. So you can look at the recording of the video later on to see it in a greater detail. Okay? So I've explained it taking cases over here, what basically are found. So I hope you will find that beneficial. So let us move to the code. There is a CACS question. We'll take that question. We'll submit over there, and yeah, it is round trip 2, I guess. Finally distinct, yeah. So there are, you can see flight connections. You can read this question. You can read this question for a while. So it's again referring to the same thing. You have n cities and m flight connections. And what are these flight connections? Basically, there is a flight connection from city A to city B. So it is directed. This particular language means it is a directed graph. There is a definite direction of this connection. We have to say, and they are one way. It has been given already. It is one way. Now, we have to state if there is a, like, your task is to design a round trip that begins in a city, goes through one or more cities, and finally returns to the starting city. Okay? And we have to say if it is impossible, it may be impossible. Else we have to return that, okay, this is the number of cities on the route, and then we have to print it. So you can see the city where we are returning 2132 means we started from 2 and we return to 2. Okay, so let us see how we can solve it. I hope the question is clear. You can search it yourself as well. So let's see. So let us copy some already done programs so that we get some templates already made. Maybe high score question. Okay. CD computer programming, CP high score. So I hope all of you would like to have this in C++. CD CACS graphs, and you can usually find all these on my GitHub ID as well. I keep on uploading them. CP CACS, okay, CP high score, and what is this problem? Round trip 2. So we'll have round trip 2 dot cpp. Okay, so we have round trip 2 over here, and we'll not do all these things. Let us take the input. So what is our input? NM and then all the M edges. So we can basically say we can maintain some adjacency list, right? Adjacency list shall be good. ADJ suppose, and for all the nodes n plus 1, from 1 to n I'm maintaining it. Vector LL, that's it. Okay. For LL I equals 0, I less than M, I plus plus, I'll be taking as input all the edges. So I'll say, okay, take A and B, C in A and B, and then we can say ADJ of A dot PBB. Okay, fair enough. Now what can we say? That maintain something as visited, vector LL, visited, and this visited array will have 3 states. So it will be in LL, and they will all start from 0. So I started everything from 0. Why n plus 1? Because I am taking from 1 to n. That is why I just declare the size to be n plus 1. Now I have to also return it the path to the path for this cycle. So what is important? Can we say that just for every node, if I maintain what is going to be the previous node, that will suffice? Like we can travel to the previous nodes and we can get the entire cycle. So let us try to do something like that. We will say that for every vertex, we'll maintain these previous nodes. Okay, we'll have some previous nodes and let that be 0. Okay, initially. Now we will do something like this, that for LL I equal to 0, I less than I equal to 1, I less than equal to n, I plus plus. I'll consider every node as a root and I'll try finding a cycle. Okay, a root I'm taking it doesn't mean that this has to be involved in the cycle. I can start from here, I can go to a node which can like form a cycle and then come back and tell me, okay, I found a cycle. That may also happen. Okay, and I'll keep some variable, some global variable bool flag, and I'll say that flag is false, means I have not yet found a cycle. Something like this, flag equals to false. Now what I can say is try taking this as a root only if visited I will be in state 0. If it has not been visited, then only try it. So we can say explore, or we can do something like DFS, and we'll be sending the necessary information. What is the necessary information? The current node, which is I, then you have the adjacency list, which is ADJ, then you have the visited, that is a state, and then you have previous. Okay, so while you call this, one habit you can make, that whenever you're calling a node, mark what is the previous node for it. So for the time being, you can say, okay, my previous is nothing but I myself, because I'm starting from here. What can I declare as my previous? Let me say that my previous is I myself. But later on we will focus on only we will try to see if for every node we can find its parent. Okay, we'll try to do that. Let us see how we do that. So this is the DFS, thin and simple. Current value, adjacent, and okay, we don't need the parent explicitly. Let us see how we can do it. So DFS, so this can be void DFS. I will say LL car, I will say this adjacency list I have, right? So I will pass it by reference. So I can take it over here and I'll pass it by reference, and then I'll have something like this. We have viz and we have prev. So we have viz, visited, and we have previous over here, prev. What next can I say from here? If it has already been visited, then we are not going to call it. Let us handle that in calling time. Okay. What will we say? That for all its visit all its whatever you have as its children, or to whatever it is pointing, visit all its all the neighbors. And then if you see if visited y, if it has not been visited, then do visit it. What will you do? Previous of that y is going to be what? It is going to be car. And if it has been visited, if that guy has been visited, else if you have visited and it is still alive. If it is not alive, that is, if it is in state 2, that means you will say that okay, continue. I don't want to discuss with this because the node will say that the node does not want to deal with this particular node. Node does not want to discuss with this node whether it can form a cycle. Okay, I'm not talking about myself, I'm talking about the node. So node ये कहेगा कि ये इस state से अभी कुछ नहीं मिल सकता. So I won't do another time DFS on it. And next time it says that okay, I'll try something like this, but when I'm entering over here, it is necessary that I make sure that now its state becomes 1. Now it is in the state of visited and alive. Now we will do all these things and we will say that if it is in the state of 1, then what do we know? If it is in the state of 1, that means we have found a cycle. So we will just say that means we have a cycle. So we will just return it. So we are, so just we can say flag is equal to true, and we can say that previous value of car is going to be, previous value of y, we can mention that this is equal to car. What will this indicate? That now we are getting the entire thing. So we can maybe mention it as LL flag equals to 0, or we can say that this flag is, when it is 0, this indicates that there is no vertex till now found. But when it is over here, let us say it indicates that flag is equal to y. Why are we doing this? Because now using this y, we can keep on coming back and we can get the entire cycle from here. Okay, that is why I'm storing this. Now what can I say? I can say outside this, I can keep visited of car is equal to 2. Okay, and I can do this entire thing. I can come over here and I can say if flag has some value, then it will be yes, otherwise it will be no. Otherwise you have to print no. So you come over here, you have impossible, so you can print impossible, cout impossible. Okay, and del. And for flag, what can we say? If something has been found, let us form the journey from there. Vector ll path. Okay, and path, first of all, we'll keep the last one. So we are going to continue through the previous links. So we are going to form the reverse cycle. Keep that in mind. So we'll keep the flag first, and then we will say that ll car, you can say car is the flag, and then while car is not equal to the target that we, basically the flag that we formed, or we can say the previous of car is not equal to the flag, we are going to continue. We are going to write something like this: path.pb, or we can say car is equal to prev car and path. Okay, I think we can mention car over here. Then we can say that we have got it. At the end, just the opposite thing, pb car. Instead of car, we can also say we should say flag. For ll I equals to path dot size -1, I greater than equal to 0, I minus. Now what shall we say? Let's go on printing this. Cout path I. We are printing this in the reverse manner. When we come outside, we'll say cout and del, and let's try to run it. Let's try to run this code. Round trip 2. then we will take this 4 5 2 3 4. We should get 4 2 1 3 2. So for that reason, another thing is essential. You should print the length of this path first. So path dot size, you should print this, and then now you can say dot slash a dot out. Okay, it prints impossible. Let us see why. Okay, we did not do DFS from here, that is the reason. So we just need to do DFS from here. Y ADJ visited and prev. These are nothing but pass by reference. Okay, now we can again check it. Yeah, 1 3 2 1. Let us see. 1 3 2 1. Yeah, this is a cycle. From 1 we can reach 3, from 3 we can reach 2, from 2 we can reach 1. So it is actually detecting this cycle. Let us submit it and let us check it whether it is passing all our cases. Round trip 2. Runtime error. Let us try to see why it is having this runtime error. Maybe the recursion call stack is very large. That can be the reason. Yeah, 10 to the power 5. That's way too many nodes. But still, let us see if anywhere we are running into infinite loop kind of a thing. One thing we can say is that whenever we are getting this, whenever we are getting something in flag, just return. Don't do anything else. And this we can just write in everywhere. We can just write it below over here as well. That if we have got something inside flag, if flag is some value, then just break it. Here we'll write break, not return. Okay. And now we can, this will run. Maybe the other cases we can try. 1 3 2 1. Let's try the other cases. So we'll have round trip 2. Yeah, so you can see now we are actually reducing many computations, and that is the reason. Maybe we were entering into some cycle. So see, what I've done over here is nothing too fancy. What I said is the moment you find a cycle, just close it over here. The moment you find a cycle, mark what is going to be the vertex, one of the vertices in it, so that using prev you can find the entire cycle and then go on returning. If you don't do this, the problem is that maybe some other values may get stored over there, and maybe what can happen is when you find out the previous values, it can go on recurring. It will never get back to that particular node. So many erotical things can happen, and in order to avoid those things, what we are doing is we are saying that whenever you find flag, just break the process, don't do anything else. This is where we are saying that if flag, then return. And if once it is returned and it is basically if it is having some flag value, if it is having some flag value, then it is going to break it right over here. Make sense? So that's all about the session. If we re-look at the code, what we have done is we took the inputs, we created two vectors. One was for storing the state of every vertex. Another was that if it has been visited, who is the parent. First time when we are visiting a vertex, maybe we are visiting it right from there. So that is a root. If it is a root, just mention it as I. If you mention it as -1, then also nothing is going to be affected. Okay. You can mention it as -1 also, then also it is going to pass. I can show you for this particular case. If I keep it as -1, then also this is going to pass. Yeah. So it does not matter like what you're placing over here. It will take you some experience to understand this. You can place anything, you can place even infinity over there. Doesn't matter. Now what you'll do is you need to do DFS, and DFS we'll see what we are doing. The moment we see that there is a flag value, which means some cycle has been found, break it. So break it means it will permanently leave this loop, and it's going to come outside and it will say that okay, if you have found a flag, then do these steps. What are these steps? These steps are telling that there is a path. In that path, you are first introducing that flag. What is that flag? That flag is the first vertex which we have found to be candidate for our cycle. We have introduced that flag, and from that flag mentioning that as cur, we are keeping on going to the previous node. From every cur we are going to the previous node, and we are keeping on doing it until some node matches with the flag. If it happens that this node is matching with the flag, we say stop it right over here. On stopping it, after we are coming outside, we are going to add this flag. Okay, why? Because the moment like where we started from, we are ending over there. So after like from here 1 we are traveling to 2, from 3 from 1 I'm traveling to 3, from 3 I'm traveling to 2, from 2 I'm again traveling back to 1. This is what I'm indicating using this. Then I'm going to print the path size, and then I'm going to print the entire path. Clear? So the main thing comes over here, which is in the DFS. Look into it, look at it for 1 minute, then we are going to summarize it. Look at it exactly what I've done, then I'm going to summarize it. Any questions? Okay, so what we are doing is we started from the current value, and these are the things you have seen them. Now what we are doing is whenever you are entering some value, you are saying that now you have visited it and it is active. Now you are visiting all its neighbors, and if you see that the neighbor has a flag of 0, if like the state is 0, if the state is 0, that means the neighbor has not been visited. So you will say I am the parent of that guy, so mark myself as the parent of that guy and do a DFS on that particular node. Then you're going to say that okay, if it is dead, then don't do anything, continue. If it is dead, don't do anything. This is the dead state. And we will say that okay, if it is the other one which is visited and it is still active, then do something like this, flag equals to I, and previous to I you have cur. Make sense? Now if flag is true or flag has any particular value, then you can return it. Okay, flag has some value means you have basically got some cycle. So after that you don't care about what else is happening. Where rest in the world what is happening, you don't care. Now you will say that okay, after everything is done, visited of card equals to 2. What does this indicate? That okay, I am dead now. I have done whatever I could. I couldn't find a cycle perhaps, and now I'm dead. So please take it back. Clear? So that's it. So these are the 3 states. I started from state 0, and I'm ensuring that when I'm entering some node, I'm marking it as alive and active, visited and active, and when I'm leaving it, I'm marking it as visited and dead, over. And while I'm visiting some node, I'm visiting it only if it is unvisited. If it is not visited, then only I'm visiting it. If it is visited, then I have the information about that node. I no longer need to visit it once again. Makes sense? I'll upload this on GitHub so you can find this on my profile, Saptarshi 1729. Okay. So that's it. I hope you enjoyed the session. I hope if you get this in the interviews, you'll be able to do well. So okay, take care, keep coding, and good luck with your endeavor. Bye. The problem is round trip 2. You can make your own submission there. You have to understand the differences.